Okay, so thanks a lot for the invitation to speak here. And this talk is based on these papers with these collaborators. And our motivation to work on this is the question, how can we formulate string theory on curved spacetimes? So this is, of course, very hard. So let's be a bit more specific. Can we at least do it for AdS5 CFT4? This is an amazing theory. It has been studied from many different angles. But even after all this time, we don't have the full worldsheet description. So how can we make progress? So the next question here is, what would Veneziano do? Probably fix the amplitude first. So that's our philosophy here. So let's talk about the process we want to describe. And we have the luxury that we have here 3 different descriptions of this process. In the bulk, we have type 2b string theory on AdS5 cross S5. And the process is genus 0 scattering of closed string gravitons. And on the boundary, we have n equals 4 super Young-Mills, and there should be this worldsheet theory that we don't know. So in the first part of the talk, I will tell you how we can find the amplitude without knowing the worldsheet theory. And we will use a little bit of the fact that we have these 3 descriptions. And then in the second talk, I want to make a small classical step towards the worldsheet theory by comparing the high energy limit of the amplitude with a classical worldsheet computation. Okay, part 1. Let's talk about the parameters of the theory. In AdS, we have the AdS radius, the string length, or equivalently alpha prime, and the string coupling. And in the boundary theory, we have the rank of the SU engaged group and the 't Hooft coupling, which is related like this to the AdS parameters. And we will talk about the weakly coupled process. So we are in the planar limit of n equals 4. And we will do an expansion around flat space. That means we take the AdS radius to be large, much larger than the string length. Or we take strong coupling in the n equals 4 super Young-Mills. So I will use the terms weak curvature expansion and strong coupling expansion interchangeably. So what is this AdS amplitude? We define this in terms of a CFT correlator, where O is the superconformal primary of the stress tensor multiplet. So it's related by supersymmetry to the stress tensor, which is dual to the graviton. And this is exactly the correlator that Zara talked about on Monday. And we will do a certain integral transform of this correlator to reach the AdS graviton amplitude, and for which we do a small curvature expansion like this. And the leading term is the flat space Virasoro-Shapiro amplitude, where STU are Mandelstams in units of alpha prime. And if you're missing the polarizations of the gravitons, that's because we left out an overall prefactor that is fixed by supersymmetry. A1 and A2 are the first 2 curvature corrections, and I will tell you how we managed to fix them. And in order to fix them, we use some general properties of string amplitudes. So I made here this list. We have the partial wave expansion, Regge boundedness, and the existence of a worldsheet integral. In this version of the talk, I will only talk more about the partial wave expansion and the worldsheet integral. So the partial wave expansion in flat space tells us that if we study the resonances of the amplitude, we can extract the massive string spectrum. So we plot here the mass level delta versus the spin L, and we get these famous linear Regge trajectories. And the corresponding concept in AdS-CFT is the conformal partial wave expansion or conformal block expansion. And the AdS-CFT dictionary tells us that in the flat space limit, the dimensions of the exchanged operators should be given by R times the flat space masses. So we can insert this relation to write this in terms of the mass level. And it was shown in this paper that in n equals 4, we have indeed operators of this leading dimension at strong coupling. Later, people used integrability to compute these dimensions at finite AdS radius of finite coupling. First, only for the leading Regge trajectory here in red, where in this case, this operator in the corner is called the Konishi operator. And these 2 papers, I think, are the state of the art in this. And they can now compute these dimensions for many more operators. So let's talk a little bit more about this conformal partial wave expansion. We get this by applying 2 times the operator product expansion to the 4-point function, and that lets us write the correlator in terms of the OPE data, dimension, spin, and OPE coefficients. And if we take this conformal block expansion and apply our integral transform to go to the AdS amplitude, we get the following polar pole structure for the curvature corrections. So they have poles up to order 3k plus 1, and we can explicitly compute the residues here. So we know the pole structure up to some unknown OPE data. So let's now go to the worldsheet integral. So we typically map the worldsheet to this Riemann sphere with insertions at 0, z, 1, and infinity, and get this formula for the flat space amplitude. Now, if there's a worldsheet theory, the curvature corrections should also have a worldsheet integral. The only problem is we don't know what is the integrand. But we can find out a bit more how this integrand should look like by studying a nonlinear sigma model where we expand the AdS metric in a small curvature expansion. And what we get then is something that looks like flat space string amplitude with additional insertions of graviton vertex operators, where we take the momentum of these additional gravitons to be soft. And by studying the soft expansions, we see that this integrand should be single-valued multiple polylogs of weight 3k. And this fits perfectly with the pole structure that we saw on the previous slide, because the maximum poles you get with weight 3k functions are these poles of order 3k plus 1. You can easily see this by acting with the S derivative on this function. So on the left-hand side, you increase the order of the poles in S. On the right-hand side, this produces a logarithm in absolute value of z. Okay, so let's make a plan how we can fix these curvature corrections. We attack the problem from 2 sides. First of all, we use the conformal partial wave expansion to fix the pole structure of the curvature corrections. So this has unknown data in terms of the OPE data. And on the other hand, we make a single-valued ansatz for the worldsheet integrand, which has also unknown coefficients. But by equating the 2 expressions, we can fix the coefficients and get an answer. And then to make an ansatz, we made some assumptions. So luckily, there's a lot of data available to do checks. And so we will compare the dimensions of massive string operators to the results from integrability. We can compare the OPE coefficients for exchange of a Conici operator with results from numerical conformal bootstrap. The Wilson coefficients in the low energy expansion can be compared to results from supersymmetric localization. And then in the second part, we consider the high energy limit and compare it to a classical computation a la Gross and Mende. And I find it quite amazing that these things, integrability, conformal bootstrap, localization, they are all very different and very hard computations. And they are now all connected in a very concrete way by an amplitude. Okay, so before we make our answers, let's talk a little bit about the functions we will use. These are the multiple polylogs defined as the iterated integrals. And the locations of these poles here depend a little bit on what we want to do. In the first part of the talk, we insert the vertex operators at 0, z, 1, and infinity. So the poles will be at 0 or 1. They are also called harmonic polylogs. And in the second part, we will keep the locations generic. The properties are like this. We have these differential relations where W can be a word, so it can contain multiple letters. These are multi-valued holomorphic functions, and evaluated at 1, we get multiple zeta values. For example, if the labels are 1, we get the power of log 1 minus z. If the labels have several zeros and a 1, we get the classical polylogs. The single-valued version of these functions has been constructed by Francis Brown, and they can be written as such weight-preserving combinations of the holomorphic and anti-holomorphic multiple polylogs. And the coefficients are fixed by demanding that they satisfy the same holomorphic differential relation and that they are single-valued, most importantly. So they're non-holomorphic, and evaluated at 1, they define the single-valued multiple zeta values, which can often be used if you do a computation and you see these single-valued multi-zeta values. It's usually a hint that something single-valued is going on. The examples, when you have ones, we get again the power of log, but now with an absolute value in the argument. And the other example is the single-valued version of the dialog. Note that this is not symmetric in Z and Z bar, and correspondingly, the anti-holomorphic derivative is a bit more complicated. There's also always one term where you remove the rightmost label and get a pole, but there are also some other terms. Okay, now we are ready to make our ansatz. The first formula I already showed you before. If here for A, the integrand is G total, but to make the function manifestly crossing symmetric, it's beneficial to write it as a sum of 3 terms with the function B of these arguments, which has its own integrand G. In flat space, the integrand is just G total is equals 1. And remember that I argued that the weight of the integrand should be 3k. So for the first correction, it's weight 3, and demanding consistency with the pole structure from the OPE fixes the coefficients. And for the second correction, we get something of weight 6. And we use these symmetrized polylogs to make the function B crossing symmetric. I mean, we make it symmetric under exchange of S and T manifestly. Okay, so we made some assumptions by writing down this ansatz. So let's come to the checks. The first check is concerning the OPE data. So in a strong coupling expansion, we can compute all the OPE data in these 3 boxes here. And for instance, for the leading Redshift trajectory, we get this result up to order 1 over lambda. And remember that delta is the mass level, and by choosing a Redshift trajectory, each operator has also a fixed spin. And this agrees precisely with the results from integrability. And also we saw on Monday that in Zara's talk that she managed to use numerical conformal bootstrap to get tight upper and lower bounds for the OPE coefficient of the Konishi operator. And we saw in that talk that this also precisely agrees with our result. And it was very important to include all 3 terms to get a better match. The second check is regarding the low energy expansion. This is the small S and T expansion of the amplitude, and it makes contact with the low energy effective action, which is supergravity plus derivative interactions. And the expansion of the amplitude looks like this. We have supergravity plus crossing symmetric polynomials. By writing out some terms of the expansion, we can identify the corresponding interactions in the low energy effective action. And the alpha zeros are the coefficients that are fixed from the flat space amplitude, and we managed to fix all the alpha 1s and all the alpha 2s. Of these, 4 were previously computed by supersymmetric localization, and we get exactly the same ones. Now we can go ahead and combine our results with localization to also fully fix the d to the 8 r to the 4 and d to the 10 r to the 4 terms, which are not protected by non-renormalization theorems. Okay, so this enough for now with the checks. What about open strings? In order to have open strings, we have to consider another theory where we add some D7 branes to the mix, where the open strings can end. And this breaks some of the supersymmetry. So the best we can do is that the dual is a 4D n equals 2 superconformal field theory. And in this case, we also managed to fix the first 2 curvature corrections for the color-ordered gluon amplitude, where the leading term is exactly the flat space Veneziano amplitude. There are some interesting points about this result. The integrand is again written in terms of single-valued multiple polylogs. This is because we are still talking about curvature corrections, so we can still think about additional gravitons, which lead to single-valued functions. Also, it does not have uniform transcendentality, which is probably expected because we have do not have maximal supersymmetry anymore. Okay, so let me sum up the first part. We use the conformal partial wave expansion to fix the pole structure of the AdS amplitude. We combined this with a single-valued ansatz for the worldsheet integral, and this fixes the AdS Virasoro-Shapiro and the AdS Veneziano amplitudes in a small curvature expansion. We compared our OP data for massive strings with integrability and numerical conformal bootstrap, and we could compare the low energy expansion with results from localization. So now we can come to the second part, the high energy limit. So why is it interesting to study the high energy limit? For me, it is because Gross and Mendes showed in flat space that the fixed angle high energy limit of string amplitudes is universally fixed by a classical solution of the worldsheet theory. So this gives us an independent way to compute the amplitude, and we make contact with the worldsheet. We will see that this is agnostic to many details. Okay, so let's first see how we can get the high energy limit if we already know the amplitude and the worldsheet integral. It's simply given by the saddle point at z equals s over s plus t. And so we get an exponential behavior with this exponent. In AdS, the location of the saddle point is at the same position, so we can just do exactly the same thing. And we want to compute this exponent and also the exponent in AdS from this classical computation. Let me review how this is done in flat space. So we write down the path integral with the Polyakov action here and 4 vertex operators. And since we are only interested in the exponent, we don't care about prefactors of the vertex operators. And we can write this as a single exponent like this, and write these terms in the integral by introducing these delta functions. This gives us this equation of motion and Virasoro constraints to ensure diffeomorphism invariance on the worldsheet. And the solution is just this, where log is the Green's function on the Riemann sphere. If we plug this back into the action, we get exactly the same exponent that we saw before from the saddle point. We now insert the 4 points at generic points, by the way. How can we generalize this to AdS? We write essentially the same action. The difference is this new term where the Lagrange multiplier lambda ensures that x is now an embedding coordinate for AdS. So x squares to minus r. And we can use this relation to solve or to eliminate x0, and then we expand x mu around flat space. So the leading classical solution is again the flat space solution, and we can plug this into the equation of motion for x1 to get this equation of motion that we now have to solve to get x1. So let's write it again. We write the log in the notation of single-valued multiple polylogs, and we use the differential relations for these single-valued polylogs to integrate this equation. So to get rid of this dd bar. So from the poles, we have to add a label to the left, and for the zeta bar integral, it's a little bit more complicated because the equation is more complicated. So we get this solution of weight 3. In general, the leading solution has weight 1, and then at every order, the weight increases by 2. And to compare this to the AdS Virasoro-Shapiro amplitude, we will now insert this back into the action and write the result like this in this suggestive way. So S1, 3, 5 are functions of this corresponding weight, and I write it as a function of the ratio only. And the limit we want to take now is we take S, T, and R to infinity all at the same rate. This doesn't touch the functions because they depend on the ratio, but we see that the first term is the flat space exponent, which dominates. The second term stays constant, and all other terms vanish in this limit. So the high energy limit of the AdS of this AdS amplitude depends only on this weight 3 correction. And we can compare this to AdS Shapiro like this. So we have the integrand for the first and second correction, and we find that it agrees. And since this is an exponent, it also means that the second correction at the saddle point is 1/2 the square of the first correction. Note that these are quite long expressions in terms of weight 6 single value multiple polylog. So this is a non-trivial check. So just to reiterate, our result is the high energy limit defined like this. It's the flat space high energy limit times this exponential correction. So let me sum up about the high energy limit. We compared it to a classical computation a la Gross and Mende. This gives a relation that is agnostic to many details like fermions and prefactors of vertex operators. And we got this result that is valid to all orders in S over R. Note that I here wrote the exponent as E epsilon open or closed, because an analogous equation holds also for the AdS Veneziano amplitude. The exponents, which are weight 3 single value multiple polylogs, for open and closed strings are related in this way, and this is exactly the way you would expect from a reflection principle. And this is also the same relation that the flat space exponents satisfy. This was discussed in a paper by Gross and Manes. Okay, so here are some future directions. One can ask if there is a relation between open and closed strings beyond the high energy limit, something like KLT or something. I'm not sure about that because we don't expect that in AdS vertex operators factorize. I mean, closed string vertex operators factorize into open string vertex operators, but maybe there's still something to be found out. We're working on doing the same in other AdS backgrounds, like type 2a string theory on AdS4 cross CP3, which is dual to ABJM in the 't Hooft limit. And we would also like to understand if we can go beyond the small curvature expansion. Maybe the high energy limit is a good starting point for this. Finally, it would be great if we could eventually compute this directly from string theory. And we saw last week at strings that string field theorists are confident that they can do this computation. Thank you.
Thank you, Tobias. Questions? Yes, over here. Wait.
Thank you for the very nice talk. I'm wondering if you have some understanding about the prefactors that appear in the weight 3 insertion. I mean, is there some particular reason why we might expect these prefactors to turn up? Thank you. In the worldsheet integral, the weight 3, the weight 3k.
Oh, you mean the polynomial and
yeah, the polynomial.
I mean, we also assume the degree of the polynomial, and this we know something about this from dimensional analysis and by what we know about the low energy expansion. So we, or you mean, yeah, part of the ansatz.
Oh, so in principle, every polynomial at the right degree might appear, right?
Yes, we assume that this is a homogeneous polynomial of degree 2, and then all the coefficients are fixed. Yeah.
Okay, thank you.
There was another question.
Maybe you said it and I missed it. The analogous formula for AdS Veneziano amplitude, will it have comparable form of these G factors, or is there a simple map between the polylogs here and the Veneziano counterparts?
Yeah, it will have similar terms, and then there are lower weight terms, and every time you decrease the weight by one, you have also decreased the weight of the degree of the polynomial by 1.
Okay, thank you.
Last question by Lance.
So what's the barrier in going to G3 and weight 9? And do you need more data, or do you need to find some patterns in the lower ones, or?
There's not much of a barrier. I mean, we just had many more interesting things to do.
Okay.
Okay, so I think we have a quick announcement before saying thanks to Tobias again.
Yeah, so we have, hello? Yeah, we have two quick announcements. First of all, the t-shirt sale for the leftover t-shirts is starting out here right now at 3:30. And the other announcement is about the luggage drop-off tomorrow. So I know that many of you will be leaving your accommodation tomorrow morning. So we'll have luggage drop-off in Rubenstein Commons, where we were on Monday for the reception, meeting room 4. And there will be someone, I think Lisa will be there starting at 7:45 a.m. So you can come there in the morning or whenever, drop off your luggage. But we encourage you to pick it up before 5 p.m. when the buildings close. So yeah, that was everything.
Okay, so let's thank Tobias again.